Thank you. This talk is going to be about how distributed applications can use software-defined networking to improve their fault tolerance. But before I get into the details of how they do so, I'd like to give a brief bit of context, and that is the long-standing challenge in computer science of building reliable systems out of unreliable components. Specifically, I'm looking at the setting of data centers, where a lot of different components can crash. Processes, operating systems, and machines can all crash, as well as network elements like switches and links. One approach to building reliable systems in this environment is to build fault-tolerant distributed systems. So how do applications do that today? Well, one approach would be to use something like a monitoring service, for example, ZooKeeper. Here I have an example application using a master backup pattern in ZooKeeper. This could be, for example, some shard and a key value server, or just a basic, some other kind of service. So here, the master is going to create a lease with the Zookeeper server, and it's going to periodically refresh that lease with a keep alive or renewal. The backup is going to monitor the master by sending a request to the monitoring service to observe the master. Now, the problem with this approach is that these lease timeouts are very long, typically on the order of tens of seconds. And this increases the amount of time that it takes applications to handle failures because they need to wait for one of these leases to time out. The problem with this is that this monitoring service is centralized. So if we set these timeouts to be very short, it can be overwhelmed with the amount of keep alives that it's getting. And this is an observation that Mike Burrows made in his Chubby paper, where Chubby is a service very similar to Zookeeper, that they had to set the timeout for that timeout for Chubby for one of Google's clusters to be 12 seconds, with provision for the server to actually push back and say, I need you to handle longer leases because I'm actually running out of CPU. In this talk, I'm going to explain how you can build a monitoring service that responds to failures quickly. So what are the requirements of such a service? Well, the first is that it should respond to failures quickly. And the second is that it should consume few resources in doing so. Finally, the reports of such a service should be definitive in the sense that applications can use them as the ground truth. It'd be pretty bad for a monitoring service to report a process as crashed when it hadn't actually crashed, leading to a split brain scenario in the master and backup. So how are we going to address these requirements? Well, looking at the first two requirements, the challenge was that these short timeouts were consuming a lot of resources. And the insight here is that the intent timeouts are implicitly monitoring every component of the system. There's a lot of layers of indirection, as one of the questioners pointed out in the last talk, so that these timeouts are monitoring the operating system, the hypervisor, and all of the links between the two processes. If we take a moment to break inside this end-to-end system, we can monitor each of these components individually with very short timeouts and avoid the overall wasted effort of duplicating work with the short end-to-end timeouts. And it turns out that software-defined networking actually has very useful mechanisms for monitoring these components individually, not only for the network, but also for monitoring host failures. Now, the third requirement is giving definitive reports of failures. And a key challenge here, which was touched on in the last talk, is the problem of network partitions. And the issue here is that there's uncertainty about what's going on the other side of the partition. And these things are a reality. We looked at the failure data for the data centers of a company with a major internet presence, and we found that in a data center with about 1,000 switches, there were about 12 partitions per month, most of which corresponded to top-of-rack switch failures. So how can a monitoring service deal with these kinds of failures? Well, one crazy idea would just be to nuke everything in the smaller side of the partition so that the rest of the system can make progress. But this is pretty disruptive because now you're nuking applications that may not care about a tens of seconds or 2-minute outage that's caused by something like a switch reboot. And if you're really going to go all the way, you might require these machines that have been shut down behind the switch to be reimaged before they can rejoin the system. Now, one of the benefits of SDN is that it actually allows us to implement this sort of crazy idea at a very fine grain by only disconnecting the processes that are interested in this high availability service provided by a monitoring service. Now, in the rest of the talk, I'm going to present the service that we built called Albatross that uses software-defined networking to build a fast monitoring service. So to explain Albatross, I'm going to first answer the question of how it meets these requirements, starting with how does Albatross quickly learn about failures? And for this, I'm going to break down Albatross's handling of failures into 3 different types of failures: those in the network, those of hosts themselves, and process failures. To learn about network failures, Albatross leverages software-defined networking directly. Here I have a picture of a software-defined network. There's a controller and some switches. The switches observe status events in the network and report those to the controller that then makes control decisions. Specifically, it decides how to route packets based on some policy. For example, if the link between switches 1 and switch 2 fail, the switches will report that failure to the controller. The controller, then seeing that it needs to reroute packets potentially from switch 4, it'll tell switch 4 to send all future packets through S3 to avoid the broken link. Albatross is going to use these reports to determine when there's been a partition in the network. And it's going to decide that the smallest component of the network that's been partitioned is going to be excluded and treated as failed for the system. Albatross uses SDN directly here, but it can also use software-defined networking to detect host failures. Here, we configure the host module to send keep alives to the top of rack switch, and the top of rack switch is going to monitor the end host for liveness. And it might seem like this is going to require some kind of specialized software to be installed on the switch, but it turns out that software-defined networking has this mechanism called rule timeouts, by which the top of rack switch will notify the controller when it's no longer using some forwarding rule. So if the switch has a particular forwarding rule for these keep alive packets, it'll notify the controller when the end host crashes because it's no longer seeing the packets sent by these host modules. Now, to respond to these failures quickly, it's going to need to use a short timeout, and I said that these were bad in the beginning of the talk. The reason why it's okay here is because the domain of these timeouts is very short. They're traversing exactly one Ethernet link, and you can put the host module very low in the system, for example, in the operating system kernel or inside of the hypervisor. And second, the load for handling these keep alives is distributed throughout the system, specifically in the top of rack switches. And these top of rack switches are pieces of hardware that are designed to process packets quickly. Okay, I've now told you how Albatross uses software-defined networking to learn about network and host failures. I'm not going to go into how it learns about process failures because it leverages existing work that we built in Falcon. Specifically, it uses a spy, which roughly speaking examines the interior state of a process to determine if it's making progress. One difference from Falcon is how it handles these suspected failures. Falcon kills by terminating processes or even hosts, but Albatross is going to use a different mechanism that I'm going to define next. So here again, I have this picture of Albatross, and I didn't give a good overview of this earlier, so I will do it now. Albatross has roughly 3 components. There's a manager, which is learning about these failures from the software-defined network, and it's reporting these failures to the host module, which in addition to doing the keep alive work I talked about earlier, it exposes this API to client applications through which it can learn which of its peers are working. Now, before the manager reports the failures, it needs to make sure that those reports are definitive so that processes that are a client of Albatross don't end up with split brain scenarios. To do that, it's going to install rules in the software-defined network to disconnect suspected processes. Specifically, we're going to embed a source MAC process identifier inside of source MAC addresses and block based on this identifier. Here I have a picture of a network with 4 processes communicating across 2 flows. If there's a partition in this network, say because switch 4 restarts, then these processes have their flows disrupted. Now, since there's an alternate path between processes 1 and 4, the controller can reconfigure the network to restore connectivity between these processes. However, processes 2 and 3 are partitioned. And because process 2 is in the smaller part of the network, Albatross would like to report it as failed to process 3. Now, before it can do so, it needs to make its reports definitive. So it's going to remove process 2 from the network by configuring switches 2 and 3 to no longer serve process 2's traffic. Thus, process 3 can take over without having to worry about, say, if the partition shows up again, process 2 being able to communicate with other clients. Note also that this scheme is very fine-grained. If another application shows up, say with processes 5 and 6, these processes can use exactly the same links that are forbidden to process 2 for their communication. Now, there are some other issues in Albatross, in implementing Albatross that I'm going to touch on briefly here. And the first one is formalizing the guarantees about this service. Because it's not disconnecting processes, or because it's not killing and it's not doing lease revocation, the guarantees that it gives are asymmetric. That is, it's only giving guarantees to the processes that it can communicate with. And there are some subtleties in handling these guarantees, particularly when processes on one side of the partition make progress. And this interplays very carefully in the fact that Albatross allows disconnected processes to reconnect. And one thing that we spend a lot of time in the paper is explaining some of the corner cases, how these guarantees interplay with this mechanism for reconnection. Another issue is the fault tolerance of the manager. Since it's a component of the system involved in reporting failure, we need it to be available itself. And here we leverage just the standard replicated state machine approach. One final issue is that these software-defined networking switches only have a limited capacity for storing software-defined networking rules. And managing this space is important. So Albatross employs a distributed garbage collection scheme, and it also constructs MAC addresses in such a way that they can be carefully aggregated in case Albatross needs to disconnect hundreds or even thousands of processes at once. Okay, I have now described how Albatross meets the 3 requirements that I described at the beginning of this talk, and I'd now like to explain how it compares with existing monitoring services. But before I do that, I'd like to give a little bit of detail on our experimental testbed. Here we use a virtual network, which is a set of virtual machines connected by software switches. Our software-defined network is OpenFlow 1.2 with a Knox controller. We use OpenFlow 1.2 so that we can use wildcard matching in the source MAC addresses. Our experiments use a panel of synthetic failures in the sense that we inject these failures according to our own timing. And some of these failures were inspired by the failure analysis I talked about earlier. Our baselines are Zookeeper, which I described at the beginning of this talk, and Falcon, which is a monitoring service that we presented at SOSP 2011. So the first question is, I said that we wanted to build a fast monitoring service. Is Albatross fast? And the answer is that it is. Here I have depicted how long it takes each of these services to report 4 different kinds of failures, 2 in the network and 2 at the end hosts. And Albatross reports all of these failures quickly. And that's because it's monitoring these individual components and can respond to these failures because of the short timeouts for monitoring those components. Falcon also uses this technique of monitoring individual components, so it can react to process and host failures quickly. The difference is that Falcon kills, so when we built it, we didn't extend it to kill in the network, so it hangs when there's network partitions, say caused by a switch or link failure. Now, one thing I'd like to point out is that Albatross detects host failures a lot more slowly than Falcon. The reason for this is that in OpenFlow, there's a minimum rule timeout of 1 second, and this sets a lower bound on how quickly Albatross can respond to host failures. Now, ZooKeeper responds to all of these failures more slowly, and that's because it's configured to use a longer end-to-end timeout. This is, of course, a parameter, so what happens when we decrease that parameter? Well, what we found is that handling these keep alives from leasing processes required a lot more CPU. Here I have a graph showing the percent of a dual-core CPU being used by ZooKeeper as we add more clients for 2 different configurations. One with a 500 millisecond timeout, which would give detection time on par with Albatross, and one with a 4-second timeout that was shown in the graph above. What we found was that as we added more clients to the system, ZooKeeper began to use a lot more CPU, and eventually with about 900 clients, it began to drop the connection of some of the clients that were being monitored. Albatross, on the other hand, uses very little CPU at the manager because the manager isn't involved in the specific monitoring of processes. It only deals with the problem, with the relatively rare case when there is a failure, and that's when it has to process and send messages. This is by design because Albatross pushes all of this monitoring to the edge of the system. So how does Albatross's resource look in the system? Well, here Albatross does use some amount of CPU at the end hosts. Most of this is for sending the keep alives to the top of rack switch. And I'd like to emphasize that this CPU cost is shared across all processes at that end host. That is, this number isn't going to increase as we have more processes. There's also some bandwidth that's sent at the end host, but this is pretty small, 3 or 4 orders of magnitude less than the capacity of a gigabit internet link. And none of this traffic makes it into the trunk of the network because it's dropped by the top of rack switch. The manager itself also has a small amount of traffic, but this is mostly sending and receiving control information with the SDN controller. So now that I've compared Albatross with actual services, I'd like to give a bit of more conceptual comparison and related work. Specifically, there's been a lot of work that I would classify very broadly as a monitoring service, and this stuff has gone under different names, such as lease servers, lock servers, group communication systems, and failure detectors. And a lot of these services offer things beyond what Albatross does. For example, giving you total ordering of messages being sent or some metadata directory which you can use for application configuration. Another broad line of work that's similar to Albatross is network monitoring. However, most of this work is focused on giving information about failures to network operators and not to processes themselves. One piece of work that I'd like to call out is the work by Shaikh et al. For monitoring OSPF networks. And we were inspired by this work, particularly in the manager's decision for determining when there's a partition and which partition to treat as crashed. There's also been some work that looks at the intersection of distributed systems and networking, for example, using Paxos to apply updates to a router in a consistent order, and more recently using distributed system techniques to apply software-defined networking rules atomically across a set of switches. To conclude, Albatross leverages software-defined networking to quickly learn about host and network failures. And it also uses software-defined networking to install fine-grained rules to make its reports about failures definitive. Finally, the last point that I'd like to make is conceptual, which is that Albatross suggests that software-defined networkings are useful to more than just network operators. That is, we think that if applications allow themselves, and networks allow these interfaces to be exposed to applications, new and interesting services can be built. I'm now ready for questions.
Kostin Raichu from Polytechnic Bucharest. Great talk, I enjoyed it. So the question is, in the SDN world, there seems to be consensus that people are not really deploying OpenFlow, or if they are, they're not really using it the way we thought they will use it. So what's happening is people deploy OpenFlow in the hosts, as in Open vSwitch, and then they use the power that gives them, and they still run, OSPF and everything else in the network, because putting a centralized controller to control your network doesn't really work. So my question is, in this sort of SDN v2 approach, like Scott Schenker is branding it, do you still have the tools you need to make Albatross work?
So there are a couple ways to look at this. One thing that we do in the paper is we very explicitly explain the interface that we expect from the network that's sort of separated from specifically the OpenFlow interface. So I don't know the particulars of SDN 2.0 and what that reveals, but if we could take that interface and implement the requirements of Albatross over that, then the porting would be conceptually easy. If this isn't able to be done, another thing to potentially consider would be to push the enforcement out to the end hosts. But now the enforcement would require something like tracking which processes are looking at which other processes, and you'd end up with something that looked a lot like the group communication systems of the 80s, where you're requiring this end-to-end mechanism to make sure that communication isn't happening. And one of the advantages of this approach is now you only need to talk to one or two switches, which is going to take a lot less time than talking to tens or hundreds of end hosts.
So I imagine you get link failure notifications from pretty much any networking equipment out there, but I doubt you'll get rule expire notifications.
Right, so we worked with what's available in the OpenFlow spec because we didn't have access to enough hardware to do really anything like that.
Thanks.
Steve Hand, Google. I had a very similar question about using hardware, but I have a second question. ZooKeeper seems to use a lot of CPU. Did you investigate why that happens? It's so surprising.
No, we didn't actually go into the details of what was happening with that particular experiment. I do know that it seemed like the main issue was that these timeouts were largely caused by the clients not being responded to within the 500 millisecond or whatever they were expecting on that end, and that was the reason why they were disconnecting. I'm not sure how much additional tuning you could get there, but what we were looking here was mostly to see if we could get a result similar to what Mike Burrows was describing in Chubby.
Sure. Yeah. No, I just know there have been a few systems recently using data center-wide RPC servers that can do scale up to allegedly tens of thousands of machines.
Yeah.
And Zookeeper seemed to be way off. So I was just curious. Thanks.
Okay.
Hi, Alisson Bessani from the University of Lisbon. Great work. I have two questions related if we try to deploy this on an SDN-enabled network. There will be two issues that I could see only by the talk. Is that one is what's the amount of events that you'll be generating to the controller? I mean, if there are some scalability limits for this, because controllers, even distributed controllers, struggle with a lot of events. And another thing is that if the Albatross control application or network application can be deployed together with other applications that do load balancing or other things that the network already need.
So the first question is, one of the issues with software-defined networking in general that's been pointed out is that the controller needs to handle a lot of control events, and these are different from the failure events that I talked about on my slide explaining software-defined network. This is for things like seeing a new flow and installing that new flow. There's been a lot of proposals, as you've said, looking at this particular problem. What Albatross requires is only this failure notification to be propagated back to the controller. So long as my link is down or my peer is no longer responding, so long as those messages are sent to the controller, we can implement Albatross. It doesn't matter if the switches are making their local sort of flow establishment decisions, so long as we can install these rules to block particular traffic, and that supersedes all other rules, we'll be okay. Your second question, I think, corresponds to the fact that a lot of the decisions in the software-defined network correspond to something more like policy than actual routing. And here you might run into a scenario where Albatross believes that there is connectivity in the system, but there actually isn't connectivity because the path is not allowed by policy. And so that would require sort of giving Albatross more information about the policy of the network and giving it sort of, instead of the physical topology, some sort of policy topology. This is something that we didn't do, but it's definitely acknowledged as something that would need to be done.
Malte Schwarzkopf from Cambridge. So maybe I missed something, but you seem to assume that when a failure happens, you can still talk to all the switches. So what happens if your network gets partitioned and a whole bunch of switches get cut off and your manager is in the other partition so that you can't install a flow rule? You can't install the rules there.
Right, so here in this example, I didn't point this out, but you'll notice that in the failure that we have occurred here, the manager is only communicating with one side of the network. It'd be fewer rules to install to just say to switch 2, don't send, or switch 4, don't send any of switch 2's traffic.
But you only have one switch in the switch 4 partition. What if there's 5 in there and they can still talk to each other?
If there's 5 in there, then all
right?
of the sort of uplink or further in the trunk switches would need to have the rules to block that traffic installed.
But between them, the partition can still talk, and they can still do silly things in their part of the world.
Right, and this is sort of the issue with the formalized guarantees that I discussed here, and in terms of reconnecting processes. So I didn't have time to sort of go into the details of what's going on there, but we spend a lot of time in the paper talking about sort of how to deal with nonsense that happens behind the fail.
Cheers.
Okay, thank you very much.